All right. So we'll do one final example now of using the gradient in a geometric way. All right. So now, in this case, we're going to suppose we have two surfaces that intersect each other somewhere. And when two surfaces intersect each other, they make a curve. And then we can ask, what does a tangent line to this curve look like? Now, hopefully these two surfaces are bad enough that you don't want to try and plug one equation into the other and see what happens. Sometimes you can get sometimes you can get an equation for a curve like that, and then if you can do that, you can just take the derivative of the curve at that point, and that's not too bad. But you might be in a situation where finding that is really bad and hard. So in that kind of a case, what would you do? Well, so what we know here, what this situation looks like, is we have a hyperboloid. Okay? And then we have a sphere. And this should be a good approximation of that. Right? So we have this hyperboloid and we have this sphere. And maybe I'll add in one of these little equator things to the hyperboloid. Right? Now, these guys intersect each other, of course, in more than just a point. We actually get a circle up here and down here. Right? But what we're asking is, so these are the curves of intersection. Now let's say the point 1, 2, 3 is this one. Right? What we're asking is we want the tangent line at that point right there. So how can we find that? Right? So that might look, something like this maybe. A little bit more. I'm very good at making a mess on this board today. So the tangent line might look something like that. So we want to ask, how can we find that? Well, since I've cleverly used up all my colors here, let's go back to pink. We need a tangent vector to that curve at that point. But if we don't have a parameterization of the curve, we can't just take a derivative. But all hope is not lost. What we do know is if we take the gradient of the function for the sphere, we get something looks kind of like this. And if we take the gradient of the hyperboloid function, we get something like this. So maybe I'll call this gradient sphere and gradient hyperboloid. So the gradient of S, so what can we do here? Well, this curve of intersection lies entirely on the surface, the sphere. So if we take the gradient of the function for the sphere, since that's perpendicular to the sphere, that means it's also perpendicular to the curve. Right? And likewise, the gradient of the function for the hyperboloid is perpendicular to the hyperboloid. In particular, it's perpendicular to that curve of intersection, because that curve of intersection also lies on the hyperboloid. So what that means is both the gradient of the sphere and the gradient of the hyperboloid, they're both perpendicular to the curve of intersection. But we want something tangent to the curve of intersection. So what can we do? Well, if we take two things which are perpendicular to it and take the cross product, since there's only one more direction left, which is the tangent direction, that means the cross product of the two has to be tangent to the curve. So that's what we'll do now. That's how we solve this problem. So the sphere, we named this function S here, so let's keep it. The sphere is given by x squared minus y squared, or sorry, I'm doing the hyperboloid. Wanted to call that h. Right? So h is x squared minus y squared plus z squared. Okay? And the hyperboloid itself, of course, is h equals 6. All right? And then the sphere is x squared plus y squared plus z squared. All right, and then now we take the gradients. This will be 2x minus 2y and 2z. All right, and then of course we want that at 1, 2, 3. We get 2 minus 4, 6. Okay. Now the gradient of the sphere function, that is just 2x, 2y, 2z. And again, we're going to take this at the point 1, 2, 3. And this time, we just get 2, 4, 6. All right. So now we need to take the cross product of that, because that's going to be the tangent vector to the curve of intersection. All right. So, so let's call the tangent vector, let's just call it v to keep things simple. So you want h at 1, 2, 3, cross product with the gradient of s at 1, 2, 3. Okay, so we have I, j, and k. 2 minus 4 and 6, and then 2, 4, and 6. Right, and then we do this, and we have negative 24 minus 24. Okay, and then 12 minus 12, so 0 here. Or actually, I'll write it in here. So 12 minus 12. Right, and then 8 minus negative 8. Right, so this is minus 48, 0, 16. Right? Now, an interesting thing here is we just need some vector that's tangent to this. So if you really liked, you can pick something that's slightly nicer in numbers, but it's not such a big deal, so we won't do it. Right? We just need something in this direction. So, I mean, if you like, you can divide this by 8 and get, what is that, negative 6, 0, 2 is also going to work. But we'll leave it here. So then the tangent line, right, L of t, so it's going to be the point on the line, 1, 2, 3, and we make it a vector, plus t times that direction. Okay? And you can leave it there, or we'll combine it here to 1 minus 48t, 2, well, just 2, actually, and 3 plus 16t. Okay? And that's it for this problem. So just remember, the goal here is you find the gradients of the two surfaces, and since the curve of intersection lies in both of those surfaces, both gradients are perpendicular to it, and therefore their cross product must be parallel to it, or tangent to it, in other words. Okay? And then it's just, you have a vector, you have a point, you can make a line. Right? That's all for the gradient and directional derivatives, and see you next time.